In construction of the Carnot-Carathéodory distance on Heisenberg group, we work with horizontal curves, those whose velocity vector lies in the span of x and y. We have seen the distance from the origin to a point on the t-axis are given by square root of absolute value of t, very different from the Euclidean case, and that by left translation, similar picture holds elsewhere in the Heisenberg group. It also turns out that if you have any Lipschitz curve into Heisenberg group H1, per definition, there is no horizontality requirement here. It's just a Lipschitz curve into a metric space. It turns out that it's also horizontal, so its derivative almost everywhere belongs to the span of xy. People often use the description that we are punished if we go off the horizontal plane in the Heisenberg group, that the length of curves become immediately infinite as soon as we leave the horizontal plane. But I like to give a description that is reward-based rather than punishment-based. And that is, when t is large, when t is much bigger than 1, in fact, it is the square root of t that is much smaller than t itself. So in some sense, distances are shorter for large-scale picture. And the reasoning behind that I've learned from some lecture of Professor Young that I am going to actually play some parts of, is that, okay, when you have a curve in R3 which joins the origin to 0, 0, t, its length, for the purpose of calculating the DCC distance, will be computed in a Subramanian metric G. So if we think of the length of curves as cost, then these vectors are each $1. And you would rather buy many x and y's for your money compared to t's, because from the Euclidean picture, these have really huge t components. So if you are here and this is vector x, this is really large in t ascent, and then but you only pay $1 for it. So from the Euclidean point of view, the length of this would be 1 plus 4y squared, but from the geometric point of view, its price is only $1. So by going away from 0, 0, by having a curve go farther from 0, 0, you have access to these big vertical ascents for very cheap price. And therefore, not that you have to, but it's efficient and it's economical to have a spiral rather than travel upward vertically. So let me orient you toward understanding what Professor Young will explain in that video. We have a different description of Heisenberg group, in fact, that is the basic definition in many textbooks, and that is through upper triangular matrices. So I put it here as an exercise. This is a fun exercise that I've done myself before. Takes some thinking, but at the end it's quite rewarding to get that isomorphism. So H1 with this weird multiplication that we had with this summation in the last component is isomorphic as a group to just matrices with the usual multiplication, which is good because then we have some idea of where this weird multiplication comes from. If you multiply the two matrices of this form, you will get x plus x prime in the apparent component. Here you will have t plus t prime, but plus something that also depends on x and y. So that will have analogy to the multiplication of h1 that we have seen before. And one other advantage of this is that we can now easily talk about a lattice within this group. So we can talk about the subgroup where all the elements are integers, and we single out these very simple ones with only one of the xy_t's being equal to 1 and the other being 0. And we have also this commutator relationship between them. This is analog of what we had, that xy bracket is minus 4t, basically gives the other missing non-horizontal component. Okay, and when you have a group like G0 here, which is generated by finitely many elements, you can assign a graph to it called Cayley graph. And we will see a picture of that at the very beginning of the video. So here, X, Y, and Z will be the matrices ABC that I had. I had to change them to be consistent with our notation. And let's see how Professor Young explains the Cayley graph.
And if you start at any point and you move x, y, x inverse, y inverse, that's the commutator of x and y, you end up one step above where you started. The commutator of x and y is equal to z. And these spirals have a strong influence on the geometry of the graph. Because, well, for one thing, they appear everywhere in this graph. So here's one of these spirals. We have a bigger one like this, x squared, y squared, x to the minus 2, y to the minus 2 is equal to z to the 1, 2, 3, 4. We can draw a bigger one like so. In this case, x to the 4th, y to the 4th, x to the minus 4, y to the minus 4 is z to the 16. And more generally, x to the n, y to the n, x to the minus n, y to the minus n is z to the n squared. Going around a spiral, taking 4n steps in a spiral pattern is the same as taking n squared steps going up and down.
So as he beautifully explained, if each multiplication is 1 unit of length, then it's much more efficient and faster to go with for n multiplication of xy's than n squared multiplications of z. So it's not a matter of whether we can or allowed to go in the spiral shape or not. It's just better to do so. It's a faster path from the origin to z to the power n squared. So here these multiplications are genuine matrix multiplications, and again x, y, and z are the special matrices that I had just written down.
So if we take this scaling limit, those boundedly many vertical edges have to get shorter and shorter. Their length has to go to 0. And so in the limit, shortest paths in the limit can have no vertical edges because those vertical segments get shorter and shorter. In fact, what you have is you have a metric space where you can only really move in, where you have a three-dimensional space where you can only move in two directions at any given point. You have something called a sub-Riemannian metric.
So there we go. We ended up seeing the matrix representation of the Heisenberg group and its discrete subgroup as well.